doing well. I hope you're getting sleep and making progress on your work. This is these videos are going to be for the stuff for week 13, which is springs, oscillators, that sort of stuff. And I'll talk a bit about elastic deformation. I'm not going to do a whole lot on it, but you can look in the textbook for details. But basically, we're going to talk about springs. Anything that's a spring is something where, I have this paper clip here for an example. If I apply some force, it deforms in some way. In this case, it bends to one side. That's a spring. We have other types of springs, right? Rubber band. If I apply a force to it, it gets longer. So any sort of thing where you apply a force and it changes the length, and the amount of force you have to apply depends on the length, is a spring. This is what's called Hooke's law, is that the force that you apply to a spring is proportional to the amount of the amount of change in the length of the thing, or the amount of change in its position. Right? So something like a wire that bends, you can see how much it moves when I apply some force to it. If I apply more force, it bends more. So this is what's called elastic deformation, is if you bend something a little bit and then it pops back where it was. Plastic deformation is when you bend it a lot and then it stays bent. It doesn't restore all the way. So we're just talking about stuff where a little bit of force causes a little bit of change in the length or positioning. And in particular, we're going to use stuff that can stretch or that can compress. And so for that, if we apply force, it stretches a little bit. If we apply more force, it stretches more. And so I'm going to draw springs as the sort of typical coil spring. All right, so maybe we have something like this, and it'll have some rest length x initial. And then we'll ask, well, what happens when we compress it or we stretch it? All right, I wanted to get a better, there's a coil spring. So if we stretch it, you see the coil spread out. And in principle, we could stretch just half of it. And we can talk a little bit about what we mean when we stretch different parts of the spring and such. But if we stretch it, what happens? Well, we apply force. Say my left hand is going to pull upwards to stretch it. It pulls back on us. So if we make the spring longer, we would have some applied force upwards. And so conversely, we would feel a force that is downwards. So this applied force, let's say it's K delta X. K is going to be some constant. And it's positive because the direction it's changed in length here is delta X, and upwards is positive. So the spring then provides its own force. So the force for the spring, which acts on us, the third law of force, is going to be minus K delta X. And this is the bit that we're always going to deal with. This is the Hooke's law bit. And we can go and talk about it slightly differently. Let's look at a spring that's compressed. So we have this length. We're going to copy it to a much more compressed. So if this is how much it compresses, so now downwards is negative. So here we would have the applied force is minus K delta X, Actually, let's make it positive downwards this way. All right, the thing I'm trying to say is that the force that the spring puts back onto whoever's compressing or whatever is compressing or expanding the spring puts a force on it of minus the displacement times a constant. Right, so if you make it longer, if you stretch it upwards, then this force is downwards. All right, that's what the minus sign is saying. It's a vector quantity. Then, so if we compress it, and this is what it looks like, then there'll be a force upwards. So this is of the applied force. Then the spring will give a separate force, which is minus k delta x in this case. Delta x is downwards, and so the force is upwards. And so as a vector quantity, this is what's true. The vector for the force equals minus k times the vector for the displacement. Now, I'm just trying to be careful here so that you understand we're going to ask different things. One is, what is the force I have to apply to stretch the spring? It's going to be the applied force. It's going to be k delta x. What is the force the spring applies onto my finger when I stretch it? It's minus k delta x. It's the spring's force on me. So remember that. That's our Hooke's law. We can figure out something nice about it, because it doesn't matter if I stretch it a little bit or if I stretch it a lot first and then bring it back. The result is the same. I end up applying the same force and it stretches the same amount. So this is a conservative force. Which means we can write a potential energy, U for a spring. So the way we would do that is to say that potential energies look like minus the work done by the force, which is minus the integral of F dot delta x. Actually, in this case, it's dx. Right. So the way this will look is U for a spring, it's going to look like minus the integral of k, and then we have to go and say, well, what is delta x? It is delta x is x minus x initial. It is the, going back to our diagram here, this was x initial. If we stretch it up, its final position is up here, and so delta x is this difference. When we compress it, we shrink it down a bit. So it's going to be x minus x initial dx. Well, this can be converted to a different set of variables, but just as if you do this calculation, you'll get there's a minus sign inside of this because it's f of the spring, which is minus kx. So these minuses cancel, and you'll get 1/2 kx squared evaluated at x final and x initial. But the valuation at x initial should be 0. But anyway, this is the change. The change in energy is defined as this. And so the change in energy is defined as this. And so our definition for the potential energy is 1/2 kx squared. And so what that means is we can come up with a new statement for the mechanical energy. Our mechanical energy here is going to be, mechanical energy is 1/2 mv squared plus mgh, plus we also now have a rotational energy, 1/2 I omega squared. And now we have this elastic potential energy plus 1/2 kx squared. All right. So that's going to be the form of it. Now what we're going to have to do is practice a few problems where we look at these sets of equations and try to figure out what's going on. Okay. So let's go back to Hooke's law for a bit. Hooke's law is fairly straightforward. We can think of a problem. So let's say we have a jack in the box, right? So big spring, and then something that sits up here with some mass element. Let's call that 1 kilogram. So this spring has a natural length, and we'll call it, say, 0.5 meters. And we're going to compress it into a box that is 0.15 meters, let's say. So 15 centimeter box, that's like 6 inches. All right, and so we're going to compress this spring and put it in a box, and when you open the box, it pops out and goes, maybe it makes some noise or something, and the little kids giggle at it. So what we want to know is, one, what is the force needed to compress? And two, what is the energy stored? All right. So for one, that's pretty simple. We try to figure out what's going on. We also need to know this. What is the spring constants? All right. So I'm going to pause the video and I'm going to show you where to get some spring constants if you try to look them up. So this is the thing. If you try to look it up, all right, we started with potential energy here in this section, but if you try to look it up, say in the energy section, or maybe it's in the force section, though I haven't seen it. The springs are sort of constructed. They're things we make. You have to deduce what the spring constant is based on the behavior of the spring. Each spring is different. Now, some springs you can go and make and do elastic properties. You can look at, like the paper clip, I can look at the elastic properties of steel. And so there's a whole bit of this you can research on your own about, in the case of the spring I showed you, it's looking at the shear modulus, right? It is, you have, for shear, it is this thing where I have the spring, like this, and I'm trying to bend it sideways like that, and it deflects. You could also stretch it, and that would be Young's modulus, and you can try to squeeze it together, and that would be bulk modulus. So springs like this, you kind of have to deduce from what's going on in the problem. And there is more ways of doing that. When we get into oscillations, then one of the obvious ways of trying to do it is to look and try to measure the force based on the displacement. That's what the lab does. And then, you can figure out what's going on. Or when we actually get an oscillation, it's as simple as looking for the frequency of oscillation and using it to calculate the spring constant. So there's different ways of doing it, but for a problem like this, we just have to tell you. There's no real way, there's no chart you can look up. You just have to have the number in front of you. And we need to make up a number. So I'm going to say that for this spring, it's, let's say, 10 Newton per meter, let's say. That's our spring constant. Our units for springs, right, because we need to get forces and we have distance, it'll be newtons per meter. So the force we need to compress, well, how far are we going to compress it? Delta x is, well, it's the compressed length minus its natural length. Which is now minus 0.35 meters. So the force we need to compress is 10 newtons per meter times minus 0.35 meters is minus 3.5 newtons. And the minus sign here, minus equals downwards. Right, is to compress it. We're taking our measurements upwards is plus y. That's fairly straightforward. Now the second part is the energy, and the energy is easy enough. What we say is that the natural uncompressed length when x is 0.5 meters, then our energy of the spring is 0. We're defining this point as effectively x is 0. So when it's compressed, our energy so I'll call this S initial. So this is, we're trying to find the change in the elastic energy. It is final minus initial, but this term is 0. And so it's going to be 1/2 times our K times delta X squared. All right, so delta X here is being measured from our initial position, X initial. So this is going to be 1/2 K is 10 newtons per meter, and then we'll have, well, we're starting at 0.5 meters minus 0.15 meters, so it's minus 0.35 meters squared, right? Because it's delta X here. And so we calculate what that is. I don't know what it is. This says delta U, the potential energy of the spring is 0.6125 joules. That's how much work you have to do to compress the spring. And so it's the amount of work stored in the spring so you can do something useful. Right. So we're going to take this setup and we're going to ask a third set of questions. So I'm going to leave right there and I'm going to say 3. The third set of questions we need is, if we release a spring, how high will the mass go? Okay. This is an energy problem. Okay. And so I'm going to ask a fourth question. At the natural resting point, what is the velocity of the block? That's a reasonable question to ask. So we'll do 3 first. And so for 3, if we release a spring, we're going between 2 different states. We have one state that's all compressed up and one state that's all stretched out. And they both, the mass is moving upwards. So we can look at this and say, well, in this case, let's make our natural length of the spring, x is 0. All right, that's our origin. And so in this case, we have our initial energy is 1/2 mv squared plus mgh plus 1/2 I omega squared plus 1/2 k delta x squared. So it's not a rotating thing. We can drop that. And at the moment, it's not moving. V is 0. So it goes away. So we're just left with the other 2 terms. And we'll put in h initial and delta x initial squared. So the final energy, right, and I'll draw it in with a green arrow down here. The final energy is going to be, well, it's the same terms, but now it's still, the maximum point means V is 0, so that goes away. It's not rotating, so that goes away. So we'll have mg h final plus 1/2 k delta x final squared. And these things have to be equal. So that's what we can do. We can set them equal. Mg h final plus 1/2 k delta x final squared equals mg h initial plus 1/2 k delta x final, initial squared. And so now we need to start thinking, well, what is our h initial and h final? Well, h initial equals delta x initial in one case, and it's minus in the other. The idea is that h initial is negative. H initial is minus 0.35 meters, and delta x initial is the same, but you're squaring it. It's going to be positive eventually. This should be a greater than 0. We don't know what it is, but we expect it to be greater than 0. And whatever this is, h final should be delta x final. Okay. So that lets us do is start plugging in numbers here. I'm going to take g is 10 meters per second squared. Make math easy, so we'll have 1 kilogram times 10 meters per second squared times h final plus 1/2 10 newtons per meter times, and now I'm going to replace delta x final is h final. And on the other side, I'll have 1 kilogram times 10 meters per second squared times, and we know what h initial is. It was how much it compressed. It was 0.35 meters minus 0.35 meters plus 1/2 10 newtons per meter times delta, minus 0.35 meters squared. And so that's doing some math that we can organize around. So this term, actually, can we do any canceling here? We can do a bunch of canceling. We have newtons, 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 and newtons there. So all of this cancels. And we'll have meters, and this will give us a meter, and so we can drop some units. We know we're going to get something in meters. And so we'll have 10 h final plus 5 h final squared equals, well, this first term here is 3.5, and the second term is, what was it we calculated? Minus 3.5 plus 0.6125. And we can divide everything by 5. So h final squared plus 2h final is, and then this side is minus 3.5 plus 0.6125 over 5. We're just cleaning this up a bit. You see it's going to be a quadratic eventually, but it's going to have two solutions. And one of them makes sense. One will be positive, one will be negative. So one moment, please. Let's figure out what this term is. 3.5 minus plus 0.6125, and we divide by 5. And so equals minus 0.5775. So this is the case where what we would do is jump into your graphing calculator and see what it says. Or we would throw this at the quadratic formula. All right, so we can rearrange this. H final squared plus 2H final plus 0.5775 is 0. So H final is minus 2 plus or minus the square root of 4, 2 squared, minus 4 times 1 times 0.5775, all over 2. Let's check that this makes sense. 4 times 0.5775 is 2.31, minus that plus 4. Thing under here is 1.69, square root of that is 1.3. So it is minus 2 plus or minus 1.3 over 2. Have we dropped a minus sign somewhere? We dropped a minus sign somewhere. No, we haven't. Both of those are going to be negative. What happened? All right, we're going to pause for a minute and try to figure out where my mistake went. Probably you see it already, but it's blinding me for the moment, so we're going to pause and figure out what I did wrong. Okay, so I realized what happened in my problem. I said this thing had some natural length of, it's like half a meter long, but there's something, there's some other stuff going on here. This thing would have some different length if the mass wasn't connected. And so what I think what's happening is, as we went through the calculation, we're doing it right. This is the right method. But what's going to happen is we're going to get two negative numbers, which means that the spring isn't going to go above its natural length. It's going to have this mass on it all of that. But that doesn't make sense either. So, shit, I don't know. Give me a minute. All right, so we're going to try to set this problem up again because something went off. I don't know what happened. I can't find an error, but we're going to try it differently. We're going to say that the minimum potential energy, zero potential energy, is when the spring is completely compressed. And so our initial energy is just 1/2 K delta X initial squared. All right. So now we're going to say E final is mg H final plus 1/2 K. Now, how much is it stretched? Well, this is delta X initial. This is delta X final. So it'll be delta X final squared, but H final will be delta X final, that length, plus delta X initial. All right. All right. These deltas are X minus X initial. So it's initial. So we'll set these equal, and we'll have 1/2 K delta X initial squared is mg H final plus 1/2 K. So delta X final has to be H final minus delta X initial. H final minus delta X initial squared. So new way of attacking it, and we'll separate this out. This will be plus 1/2 K, and then we'll have H final squared plus delta X initial squared plus 2 H final delta X initial. Sorry, that's a minus sign there. Right? And now we'll put delta x initial on one side, and we'll put so we'll also mg h final. So we'll separate this a little bit more. So mg h final plus 1/2 k h final squared plus 1/2 k delta x initial squared plus k, so 1/2 and 2 cancel, we'll make it a minus sign, h final delta x initial. So the other side is going to be 1/2 k delta x initial squared. And so that appears on both sides. They can cancel. And so now we have a quadratic equation. Is 1/2 k h final squared is, plus mgh final minus k delta x h final is 0. And that means all those terms are 0. One idea is h final will be 0, right? Because we can factor a common 0 out, a common h final out. So one solution is it doesn't move. That has the same energy. But that's not going to work. The other one is going to be when this has a solution. And so we can figure out what it is. H final will be, so this other side over here will be minus mg plus k delta x initial. Yeah. Times, and then we'll have a factor of 2, and then we'll divide by k. Right. And so now we can do some additional math. All right. We can actually plug in h final will be minus 1 kilogram times 10 meters per second squared over 10. There's no parentheses here. There we go. Minus 10 newtons per meter. So that'll give us units of meter. And then we'll have plus delta x initial squared. So this whole thing is going to be minus 1 meter. Plus I've divided something weird here, haven't I? You know what? This video is getting boring as I'm doing algebra here. 0.35 meters squared. Again, you're going to get a minus sign. That's going to be about minus 1.6, and that's what we got the first time. So somewhere there's a weird minus sign in here. Maybe you release the spring and it just falls inwards, but I don't think that's right. That doesn't make sense. Anyway, set up these problems. And I want to end the video by going back to this. What happens? What is the speed when you get to the initial position? So maybe I've screwed this up and we'll just go through another problem. But let's see. Well, when we get to the initial position, all right, so we'll have the springs compressed, and then eventually the spring is loose and it has some velocity there. And so the initial case, E initial, is, we'll put H is 0 there. And so we'll have mgh is 0, 1 half mv squared is 0. We'll just have 1 half k delta x squared. And then E final will be mgh plus 1 half mv squared, but h is the size of delta x. It's going to go upwards. So we can solve. We can go in and say 1 half k delta x squared is mg delta x plus 1 half mv squared. And then just put in numbers. 1 half 10 newtons per meter times 0.35 meters squared is 1 kilogram times 10 meters per second squared times 0.35 meters plus 1 half 1 kilogram v squared. And so we can do some math. We can find this term, subtract over that term, do some algebra here. 5 times 0.35 squared is that minus 10 times 0.35 times 2, and we get a negative number. So something about this problem is telling us so what you're seeing here is me failing to teach this particular problem, and it's okay. Things happen. We've designed a problem. It's a reasonable problem. I've shown you the method, and what we've realized is the problem's not feasible. The weight can never get back to this equilibrium spot. That's weird. Something's went wrong. So we're going to pause the video there. You've seen the gist of how to do these problems. If you have a force problem, it makes sense. You do the necessary calculations for forces, and you find the force based on the spring constant and the distance. And if you're trying to do an energy problem, you're going to use the mechanical energy, and you're going to find it at one location and at another location. And these things get awkward. I think that's you had a problem like that in the past homework where you're trying to find the length of a bungee cord, and that sucked, and I kind of just gave you credit for it if you tried it. So the problems that you have in the homework should be easier, and we're going to go on and just have a brief video on pendulums. All right, we're going to stop here.